Did you know that standing here on Earth's surface, we know what's in the center of the planet, despite it being 4,000 miles beneath us, and no one ever having actually gone there? And we know that down to the scale of the crystals in the core. I'm going to take you on a journey to the center of the planet, where I'll show you that not all is quiet. The Earth's core is moving. We've been trying to work out what's inside the Earth for about 100 years. And our present understanding is that we have a crust and a mantle that are both made of rock. And then below that, we have the core. The core is hot, it's made of metal, it has a liquid iron outer core and a solid iron inner core. We think that's made of crystalline metal. And we have a lot of different ways of working out what's inside the core. Actually, go back to my notes for a second to make sure I'm not missing anything. We think that the inner core has existed for about 500 million years. There are lots of different methods for working out how the core looks. We have observations from seismology. We can use physics of various kinds, mineral physics, material physics, space physics, the chemistry of the solar system, and geomagnetism. My particular tool is seismology. And this, despite the inner core only being 1% of the volume of the whole Earth, it actually affects our lives on the surface every day. The layer just above the inner core, the liquid iron outer core, is the source location of the Earth's magnetic field. As well as being used for navigation, the magnetic field shields us on the surface from the rays from the sun. And the outer core is heated from below by the freezing of the inner core. As the inner core crystallizes and cools, it releases heat. And that the rate and the location of the crystallization affects how the magnetic field moves. The hot outer core material is less dense and it rises, and the cooler material is more dense and it sinks. Okay, it doesn't matter. I have hands. And so the way in which the inner core crystallizes affects how the magnetic field moves. It affects how the convective pattern in the outer core. As the outer core convects and moves, the movement of a conductive metal inside a magnetic field generates an electrical current, and that in turn generates a magnetic field, regenerating the Earth's magnetic field. Hence we call it the geodynamo. We've been using compasses to navigate for quite a while, and when on ships, people have been making measurements of the magnetic field from about 1500s onwards. And we know that the Earth's magnetic field moves, and it changes through time. There's a general westward drift of the magnetic field. The magnetic field strength also changes through time. And you may remember a news article from a few months ago about how the magnetic North Pole has moved so much that compasses had to be recalibrated. While all this is actually happening in the outer core, this is driven, the power source of this is the crystallization of the inner core. So if we want to know how the magnetic field is going to move in the future, we need to understand how it moved in the past. We don't have a record of the liquid motions, the fluid motions of the outer core, but we do have the inner core. The inner core is the solid record of the outer core. But this brings us back to the how. How, standing here on the surface, can we say anything about what's going on in the center of the Earth, despite us never having gone there? To do this, we have to use other methods. Moreover, how can we look backwards in time as well? What tells us about how the Earth has changed in the past? We have to use indirect observations. People have tried to use direct observations to drill down into the Earth to see what's actually inside, but with not very much success. There was an experiment that was known as the Mohole that became known as the No Hole because it didn't go very far. And then there was the Kola Super Deep Borehole, which reached a grand total of 12,226 meters in depth, or 7.6 miles. before the experiment had to be abandoned. The rock became so hot that the drill bit became soft and couldn't drill any further. And as soon as the drill bit was removed, the pressure closed the hole back up again. So to put that in context, 7.6 miles, sorry, the inner core's the Earth's radius is 4,000 miles, so 7.6 miles is 0.02% of the way to the center of the Earth.
And it gets that hot, that fast?
Yes, temperature increases very rapidly. It's about 40 degrees per kilometer, so it gets to about 1,000 degrees Celsius, which is what, 3,000 Fahrenheit, something like that, within a couple of kilometers, like 10, 15 kilometers of the surface. The mantle itself, mantle temperatures range from about 1,500 Celsius down to about 4,000 degrees Celsius. And then the inner core itself, the surface of the inner core is the same temperature as the surface of the sun.
Wow.
Yeah, so it's kind of hot. It gets difficult. There's a little red line here that's scaled to the size of the inner core in this figure. This red line is 10 times longer than the Kohler borehole was deep. So if we want to look inside, we're going to need a different method. So we can't travel through the Earth, nor can light waves, but sound waves can. In the same way that if you want to work out what's inside a human body, you might use ultrasound, we can work out what's inside the Earth using sound waves. But how could we put the Earth inside an ultrasound machine? Earthquakes make sound waves. After an earthquake, waves fan out in all directions, like when you throw a stone into a lake. The ripples fan out. When we feel an earthquake, a lot of what we feel are the surface waves. These are the waves that travel around the surface of the Earth. But there are also a lot of other waves that travel through the Earth, all the way through the center. And it's these that we can use to work out what's deep inside. These seismic waves travel through the Earth like sound waves, ultrasound waves travel through a body. And by analyzing the waves from earthquakes, we can take snapshots of the structure of the deep Earth. Looking at just a single seismic wave, we can understand how it carries information about the structure of the Earth. The propagation speed of waves depends on the material properties, the properties of the materials through which it travels. These wiggles at the top are a typical recording that we call a seismogram, and they show the amount of shaking that a seismometer experienced at various points in time. And from this, we can pick up and identify the seismic waves. We can measure the time it takes for the seismic waves to travel some given distance, and that allows us to work out the velocity. And the velocity of a material tells us about its properties. We can also measure other changes. For example, if the seismic wave would travel through some material with different properties, in this case a little bit faster, it would arrive before the time that it would do otherwise. And so we can look for these differences to determine the material properties of the Earth. Some of these waves travel through the Earth's inner core. By looking at these waves, we found that the inner core seismic velocities depend on the direction that the wave travels through it. Waves traveling along the pole, from the North Pole to the South Pole, travel faster than those traveling in the plane of the equator. And we can measure this by looking at seismic waves. So this is one of these seismic waves that travels through the Earth's core. I always joke to people that my job is looking at wiggles, which it actually is. This wiggle shows us that the wave traveling through the inner core along the polar direction arrives 8 seconds before the time we predict it to. In contrast, this wave that goes through the inner core arrives at the time that we predict it to. Yeah, this one is in the plane of the equator. And given that the distance that these two waves travel is the same, that tells us that the velocity of the material along this direction, the north-south direction, is faster than in the equatorial direction. We measured this to be about 5% faster. That doesn't sound very much, but these waves travel at 6 miles per second. So 5% faster is nearly half a mile per second faster. Yeah.
How could that be if the inner core is all made of the same material?
Yeah, that's the fun part. That is where we're going to next.
But isn't the Earth squished a little bit?
So yes, that is an important point, but it doesn't actually come up very much. So the Earth, because the Earth rotates, it gets like pulled out at the sides. Like if you're when you're spinning pizza on your finger, it thins out because of the centrifugal force. And so the Earth is what we call not a sphere, but an oblate spheroid, which just means it's like kind of squished. But it's not very much. It is a little bit, but it's not very much. The original explanation, the original theory to explain this was an oblate inner core. But the amount that you need to stretch an inner core to make this happen is unreal, and would not be, gravity wouldn't like it. So that's an important point, but that doesn't actually come up here. And the amount of oblateness, how stretched it is, gets smaller the closer to the center you get. So we make many measurements of the seismic wave speed through the inner core at different directions relative to the rotation axis. And these red points show all of our measurements. And we generally find that waves travel faster when they're traveling in the polar direction and slower when they're traveling in the equatorial direction. And those that don't fit the smooth curve indicate there's some other pattern going on in the inner core. Making all these measurements, about 5,000, takes a lot of looking at wiggles and clicking on things. And we refer to this pattern as anisotropy. Anisotropy meaning not the same, in contrast to isotropy, which means the same. An anisotropic material looks different in different directions, depending on what direction you're looking at it from. For example, wood is anisotropic. It is hard to break across the grain, but it's easy to break along the grain. So wood has anisotropic strength. In this case, the seismic wave speed is anisotropic. The velocity is different in one direction than it is in the other. We also find that, unlike the rest of the Earth, which tends to be concentric, the strongest anisotropy is offset from the center. It's not in the very deepest part of the Earth. It's a little way into the Western Hemisphere under Brazil. But why does the anisotropy in its location even matter to us? It's because this is what can tell us about what the inner core is made of and how the inner core has moved. Seismology doesn't only give us snapshots, it only tells us about what's happening at the moment that the wave goes through it and what the Earth looks like then. We've only been doing seismology for 100 years, which isn't really long enough to measure how things have changed. But the patterns of anisotropy tell us about how the inner core has moved from when it started growing. We have reason to believe that the inner core is a solid block of iron made of many different crystals. This is a piece of a meteorite that was probably once the core of some other planet that got destroyed early in our solar system. And you can see there are lots of crystals of iron that are all long and thin. These crystals you would describe as anisotropic. While our inner core probably doesn't look like this, a single crystal of iron is anisotropic. Waves would travel faster in one direction than it would in the other direction. But that's fine. When we measure iron in a lab, the pattern of anisotropy, this black curve, so its velocity is a function of angle, looks very similar to that which we measure seismically. So if we were to go to the inner core and pull out one crystal of iron, its anisotropic pattern would look very similar to that which we measure. But that's okay for a single crystal, that's fine. How does that work when we have an inner core that's 2,000 miles across? In order to make the whole of the inner core look similar to that, we have to point all the crystals in the same direction. If they're all pointed in different directions randomly, you wouldn't have an anisotropic pattern. You have to point them all in the same way. So we need to align the individual crystals to make them all look the same. So the inner core will all look like one single crystal. Then the whole inner core will be anisotropic. We need to align crystals to make, we can align crystals with flow. Lots of things move and flow and change direction. This is a crowd of people on Black Friday. Let's get it running. Notice how, to begin with, they're all disorderly and random, and then we open the doors, and they all start running, and they all start going in the same direction. Even the people coming in from the side end up going in the same direction. Iron crystals will behave the same way. When you make them flow, they will turn and change direction. Because of Earth's rotation, the way in which the outer core convects, we think that the inner core is most likely growing more at the equator than it is at the poles. This would create an ellipsoid-shaped inner core. But gravity doesn't like ellipsoids. Gravity will try to drag it back into a more spherical shape. This involves pulling in from the equator and pushing up towards the poles. This will align crystals. And so as the inner core grows, we'll get this pattern of growing out and pulling up as the inner core grows to its present-day size. This will end up with anisotropy in the center, all the grains aligned, the strongest anisotropy in the middle. And this will all look like one big crystal. But seismology tells us that the strongest anisotropy isn't in the center, but it's offset slightly. How can we get this given this pattern? So if we started with an inner core growing at this point, we could grow it more on one side than on the other, and that would drag the inner core away from its original center point. And so if we repeated this pattern, we'd be able to grow the inner core, translate the inner core, slide it sideways, such that at the end, the inner core would be offset from where it started. This would lead to the strongest flow being offset from the center, the strongest alignment being offset from the center, and so the strongest anisotropy being offset from the center. And this pattern, this model, while it seems a little bit wild, does actually fit our observations really, really well, better than any other model so far. And so this is what I think, and hopefully soon everybody else will think, is how the inner core grew. When we slice the inner core, we can see the growth rings of how the inner core has evolved through time. And that's how, standing here on Earth's surface, we can figure out what's happened and how the inner core has grown over the last 500 million years. And thank you very much, and I'll take questions if you have any.